So let me start. So we are going to start a fresh topic now. It is more serious lectures will start. That was just an introductory part, but that was also very important. What we have discussed so far in last three lectures or so. So it is a what we call demodulation. As we discussed last time, if I have to transmit my voice signal, which is what we call here a message signal or an intelligent signal over large distances, I need to modulate the signal. Modulate means to change a parameter. So what we are changing the parameter, as I told you, at lower frequencies, your lambda is very large. And because lambda is very large, your antenna dimensions becomes very large, which we'll also talk about when we talk about the need of modulation very soon. And your antenna size becomes very large, of the order of kilometers. So I have to carry an antenna of the size of 1 kilometer with me, and so also as at the receiver end, you also have to do, which is impossible. So what we do here, we write this signal over a carrier signal, which is a high frequency signal. And now because it is written over a carrier signal or a high frequency signal, I need to carry only a very small antenna, because high frequency means wavelength, which is C over F, is very small. And then it is transmitted. And then at the receiver end, finally reverse process start. It is called a demodulation or detection, which is the inverse of demodulation, because finally the same message has to go in a normal way. So here, as we have discussed, it is a process of changing one of the parameter. As I said, a signal has got three parameters: frequency, amplitude, and phase. Vt is equal to V sine omega t plus theta, or Vt is equal to V sine omega 2 pi ft plus theta. That was, so basically three parameters are there: frequency, amplitude, and phase. So I change one of these parameters, either frequency or amplitude or phase of the carrier signal. Okay, carrier signal is generated by me. Message is my something I can't change. I have to transmit it. And that changes in accordance with the amplitude of the message signal at every instant. So it should change in accordance with the amplitude of the message signal. So where my amplitude of the message signal is high, the corresponding parameter, frequency, amplitude, or phase should be high of the carrier, and so on. So that means I am actually superimposing my low frequency message signal to high frequency over the high frequency carrier signal. I gave you a simple example that if a child crosses the road on his own, child is like your message signal, it will be disastrous. But if a child is carried by an elderly and then the elderly cross the road, it is fine. Okay. So same thing here, the message signal is overridden over the carrier signal, and then it goes to the destination. Okay. And then the child is dropped at the other end of the road by the elderly. So that is what we call the demodulation or detection. Now here, as we see, now we are talking about the three signals in the modulation. Basically, one is what we call the message signal, which is also my information signal. And it is typically a low frequency signal. Most of the signals what are intelligent signals like the speech are low frequency signal. This is what we call modulating signal. Now, please note that we use these words quite often because now we are talking about the modulating. So this is called the modulating signal, your message signal. Then we have a carrier signal, which is a high frequency signal. Okay. That means it is a high frequency. And then when it is overridden, what we get is a modulated signal. We get a modulated signal. So what we get is final is modulated signal. So this process, so it is overridden on this, and then it gives rise to this modulated signal. So basically, this is your low frequency signal. Low frequency signal is something like this. Okay, because your time is f equal to 1 by t, and this is your complete cycle. So this is a low frequency signal. And a high frequency signal, I could actually say like this. So here my complete time period is t, and f is equal to 1 by t. So here my frequency is very large because time is very small from one complete cycle. So this is my high frequency signal and this is my low frequency signal. And what should be the waveform of the modulated signal that we have to discuss. So basically we are talking about the three signals. Modulating, we use the word quite often, modulating. So modulating means it is a massive signal and carrier is a high frequency signal and modulated signal is the final overridden signal. So it is like a this signal which I am talking about, modulated signal, it is your message signal overridden on carrier signal. So this process is what we call the modulation, mode. And the reverse process is called, reverse of this is called a demodulation, which we'll discuss also later on how to demodulate or detection. So finally at your end, you should receive my voice as I'm speaking just now. Now here, as I said, typically to start with, we assume both my message signal and carrier signal to be a sinusoidal signal to start with, because it could be non-sinusoidal also, or it could be digital signal also that we discussed. But in this course, we restrict ourselves to the analog signal or the continuous signal, not the digital signal or the pulse signal, which we normally discuss in the next course, the digital communication. So here we will only consider ourselves in the what we call the analog signal. So we talk about, to start with, we assume the signal to be analog and sinusoidal. And please note that we have last time we have seen it is given as V is equal to V sine 2 pi ft plus theta. Where is your, so this is your amplitude, this is your frequency, and this is your phase. So this becomes my amplitude part, this becomes my frequency part, and this becomes my phase in hertz, in degrees, or radians, whatever you call, and it is in millivolts, volts, or something like that. Okay. And this is my, what we call the final signal. Now, please note that this is written in small letters, your AC signals, and this is your written in capital letters because this is an amplitude. It is in a DC. So this is like a DC signal. And this we say is an AC signal. That means it depends upon the frequency and everything. So your signal is represented in mathematical form by this expression. Last time I also used VM, basically just to denote the maximum amplitude, if you recall. But basically now we keep it capital V and small v. Capital V means VM, what we discussed last time, that is the maximum amplitude at that particular point. Okay, so this is how we write this expression. So to start with, we assume that my analog signal, we are talking about the analog modulation only. And analog modulation means it implies the analog signal, which to start with, we assume that they are in sinusoidal form. In the previous slide, we talk about the massive signal. Sometimes also this is called the baseband signal or baseband signal. That is also a very popular word. Or a baseband signal. So this is also a very common word we normally use. So baseband signal is nothing. It is your massive signal, your low frequency signal, which is overridden on a carrier signal to give rise to a modulated signal. Okay. Now, how the modulated signal will look, that depends upon, I'm not drawing it right now because that depends upon what parameter I'm changing. As I said, I could change one of the parameters of the carrier signal, either frequency, amplitude, or phase. If I change the amplitude, it gives rise to the amplitude modulation. If I change the frequency, it changes the frequency modulation. If I change the phase of the carrier, it will give rise to the phase modulation. But for the massive signal, we always see the amplitude part only the amplitude. Okay. Now it means when the amplitude is high, your frequency is high. When the amplitude is high, your amplitude is high in the case of amplitude modulation. When the amplitude of the massive signal high is here, then the phase of the carrier is also high in the case of the phase modulation. So that is something we have to understand. So either of these parameters I can change, but for the message point of view, I only see the amplitude. So this gives rise to, so basically as we see here, my modulation could be of three types. before we go into the mathematical formulation of the modulation, so basically, there are three types of modulations are possible. One is, so it depends upon the modulation technique. And it depends upon the modulating technique. That means I could have AM, I could have FM, or I could have, oh, sorry, I will erase this. So here, my signal, I put in the other paragraph, modulating or message signal. And here I put the carrier signal, which is your high frequency signal. Okay. And here, parameter of carrier signal changed. What parameter I'm changing? So basically there are, so we talk about the analog, then there is a digital modulation, and there is a pulse modulation. Now in the analog modulation, we are assuming my signal to be analog. Carrier signal is also analog. Analog means CW, the continuous wave, or CW. CW, if I've already told you, it is continuous signal, not the discrete signal. It will continue, something like this. In the pulse case, in the digital modulation, we have a digital signal, so not continuous. Your carrier signal is also of digital type. And there is a pulse modulation also, which is here we call the analog. Signal is analog here, message signal, but your carrier signal is digital. So in this series, in this course, we will restrict ourselves to this analog modulation. So that means where both the analogs, where the message signal and the carrier signal are analog or continuous wave. And these continuous wave signal could be sinusoid or non-sinusoidal also. Okay. But to start with, we assume to be a sinusoidal signal like a sine omega t plus phi. You can use cos also, it is one and the same thing. So basically in this case, you get three types of the parameters you could change: amplitude, frequency, or phase. It will give rise to AM, amplitude modulation. This gives rise to the frequency modulation, and this gives rise to the phase modulation. Here also, we can change certain parameters, which is normally the amplitude, the width of the pulse, okay, because now it is pulse, and the position. Sorry. This is the digital modulation. So here also we could change amplitude, frequency, phase, which give rise to here what we call the ASK, amplitude shift king. But we are not talking about, just give to an idea. Here a different type of the modulation schemes are possible. And here also we could change either of these parameters, which could be amplitude and pulse width, because digital signal is a pulse signal. So it is a pulse signal. This is also pulse signal. Okay. So pulse width is important here. Or another parameter which I could change of the carrier is the pulse position. Pulse position. Okay. Where the pulse starts, where the pulse ends. So again, here I could get something what we call the PAM, pulse amplitude modulation, and pulse position modulation, PPM, and pulse width modulation. But as I said, here we'll consider only this part. So for us, this is something which we are going to discuss. That means analog modulation, both the message signal and carrier signal are analog in nature or CW in nature. I can change one of the parameters which of the carrier signal, which is analog signal, either amplitude, frequency, or phase. It will give rise to three types of the modulation: AM, FM, and PM. And you must be aware of these words: AM radio, FM radio, and PM radio, and so on. Okay. Other things we are not going to discuss, but otherwise it is amplitude shift king, frequency shift king, phase shift king, pulse amplitude modulation, pulse width modulation, and pulse position modulation. So these things are not part of the current course. Okay, that is a separate course. So this is what analog or CW modulation. Digital modulation or pulse modulation, we are not going to discuss. Then the other thing comes here. These two categories, because they are part of the angle, as I told you last time also, this is what we call the angle modulation also. Frequency modulation or the phase modulation is also called the angular modulation, because as we have seen in the last equation, these are part of the angle. So this is part of the angle. So this gives rise to what we call the, if either of these parameters I could change, I can say it is an angular modulation. But if I'm changing this one, it is an amplitude modulation. So basically we have two types of the modulation. Analog modulation is amplitude and angle. Within the angle, we have, as I said, we could have FM or PM. So if you see, they both are related to one another, FM and PM. So one of them we only consider FM. PM will normally don't consider, as we'll see later on why. So this was about general this thing. Then let's understand what is the need for the modulation. Okay. Now this is very important. Why? To one thing I have already told you, need for modulation. So first is important thing is, which is very, very important of what we have discussed is the need for modulation is the small size. So basically to size of the antenna. So why the size of the antenna, as I told you, suppose now I will explain to you. Now I will write here also. Let's say I got a audio tone. Sometimes we use the word tone also for the signal of, let's say, 1 kilohertz. Okay, that is the typical audio signal, 300 hertz to 3000 hertz and so on, which you have seen are the voice frequencies. Now here, this is my frequency. And for this signal, your lambda, which is what we call the wavelength, okay, it is written as C over F. So it is C is nothing, it is 3 into 10 is to power 8 meter per second. And this becomes 1000 hertz, okay, or per second. Hertz is also per second, okay. So in this case, if I see, it turns out to be 3 into 10 is to power 5 meter. Typically, as I said, antenna dimensions are related to the wavelength. Typically, we use lambda by 4. So in this case, it turns out to be 3 into 10 to power 5 meter divided by 4. Antenna dimensions are typically lambda by 4. So it turns out to be requiring an antenna of something like 1250 meter. Okay, that means 1.25 kilometer. So that is the size of the antenna I require at the transmitter end, and the same size of the antenna you require at a large impulse. So this is impossible. This is impossible. So what we do here, we transmit over a large frequency, okay, maybe some gigahertz or megahertz frequency, and bring my antenna size down, and which is, you see now your antennas in the mobile phones are very, very small. Earlier mobile phones, if you see, there were 2 protruding antennas, okay, one for transmission and one for reception when the mobile phone started. After that, now you notice they come only with a single antenna. That means the same antenna is required for both transmission and reception. Obviously, it requires a duplex operation, which we'll understand. And then finally, there is no antenna. Antennas are there in your mobile phone, but now they are embedded. Now they are embedded. Why? Because our aim is to bring the antenna size down. The mobile phone size. Nobody wants a protruding antenna. But yes, at some cost. Antennas are supposed to be outside, like your DTH antennas, your Tata Sky and other thing. They radiate very well in an open environment rather than in a this thing, because your radiation is affected if you're putting in a box. Obviously, when you're in the mobile phone, my antennas are now embedded, but at some cost. Okay, you get the advantage that it has now become so handy and so on. But ideally, the antenna should be high. So this is the yes, please.
Here it will be 75 kilometer.
For this one?
Yes,
Lambda by 4. Yes. Oh,
okay.
75. Oh, sorry. Yes. Yes, correct. So this becomes very nice. Sorry. 75,000 meter. And that means it is like, oh, I was about to give an example. So this is becomes around your 75 kilometer. Okay. Now, if I use, so this is the typically antenna dimensions we normally use, lambda by 4, like your FM radio. FM radios, 98.3 radio Mirchi, 198.3 megahertz, 88 to 108 megahertz. Typically, if I take FM frequency as 100 megahertz, center frequency from 88 to 108 megahertz that we have seen. And if I take a frequency as, let's say, 100 megahertz, your lambda becomes 300 centimeter, and lambda by 4 becomes 75 centimeter. And that's why if you see in your car or autos, the FM radios are there. It is a wire which stretches up to 75 centimeter, just to give an example that we do. Okay, so now if the same antenna, if I use a carrier of mm, uh, 1000 gigahertz, okay, or 1000 hertz, 1000 kilohertz. Now, if 1 megahertz carrier is used, 1 megahertz means 10 to power 6 hertz. So your lambda by 4 turns out to be 75 meter, but it's still too big an antenna. But if I use 1000 megahertz and carrier, okay, that means 1 gigahertz or 10 to power 9 hertz, then lambda by 4 turns out to be 75 millimeter. And that is possible. Earlier mobile phones used to be 7.5 centimeter also. Now there are ways to further reduce it to lambda by 8 or something like that. That is the antenna designs problem. But yes, this is the advantage I am getting. So basically the first thing why we do the need the modulation, the size of the antenna is too large and we need to reduce it. So I could complete this statement. And it need to be reduced using modulation. Okay, so that is the first advantage we got it. Second advantage also, which we talked about last time, when we talk about the frequency division multiplexing. So this is the first advantage, which I put it as a 1 here. And second is what we call your modulation allows FDM. That is a very big advantage. That is what we call the frequency division multiplexing. If I recall, I gave you the example of the orchestra and other thing. Various musical instruments are playing, each at different baseband frequency or message frequency, and they all need to be transmitted simultaneously. Okay, so this is it allows this thing for frequency division multiplexing. Why we do this? It basically gives me an advantage of, as we have seen discussed last time, for simultaneous transmission. I am writing for you also, of many message, or what we call even the baseband or the low frequency signals, over a common channel. So that is the biggest advantage. So basically, if I have various musical instruments playing the same frequency within the same frequency band, say 300 Hz to 3000 Hz, so I can use or a 50 Hz to 15 kilohertz voice band, or 20 Hz to, so I can simultaneously transmit over various channels having the different frequency. Okay. Otherwise, what will do? It will interfere with one another. So I assigned a different frequency slot to them. We assign a different frequency slot to various baseband and signals. So what we do here, assign different frequency slots to various message signals. Okay. and then transmitter. So like my frequency band is from 300 hertz to 3000 hertz. Okay. Now say tabla is playing at 300 and okay, another flute is playing at some other like 400 hertz, or harmonium is playing at 600 hertz. So I assign 300, I pass over a carrier of some frequency, and another one at other different frequency slot, and third one at a different frequency slot. So there is a and each is assigned a carrier. Obviously, carrier we have to assign. The same carrier I can assign. So one becomes 1300, and becomes 1400, another becomes 1500 when it is overridden. And then your interference becomes nil almost. So it becomes, so that is another advantage of the modulation, as I told you when we talk about and similarly, we could have a TDM, time division multiplexing. We assign different time slot there, as I discussed last time, or we could assign a different code also. So 000 code we could assign to one signal, 0001 we could assign to different signal. So that becomes my code division multiple SS. And as I told you, the multiple SS is nothing. It is a last time we discussed, it is a variation of multiplexing. It is a variant of multiplexing. So this is an SS technique. What type of multiplexing you are using? So FDMA, TDMA, CDMA. So that we discussed last time. So that is the another advantage. I got it. The third advantage, which is also equally important, I put it in the red color only for your. Which is the obviously, as we have seen, now we can assign different frequencies to different this thing. Your interference and other things are minimized, because now they are having a different time slot, they are having a different frequency slots, and so on. So your it minimizes, I won't say it will totally nil it, the effect of noise and distortion. As I said, interference is something. Distortion is because of the signal itself, as we discussed in the first or second lecture. But we are going to discuss in a big way after this modulation part, the noise, disturbance, and interference. So these things are very much minimized because of the modulation. So basically, your modulated signal, they occupy your high frequencies spectrum, because it is a carrier. It involves a carrier. So where the effects are to the distortion are minimum. So you can say modulated signal are high frequency signal, because they are carrier on which the message signal is overridden. So this is a high frequency spectrum where effects of channel noise and distortion are minimum. I won't say they are zero, but they are less. Your reflection, your refraction, your diffraction, your scattering, all those parameters which are there are typically very less in this one. Okay. Then the fourth one, which is also very important, the complexity of the system. Modulation makes, I would use the word system design. System means the transmitter and receiver design simpler and less complex. That also is possible. We discussed why. Just to see this thing, let's explain to you through an example again. So I take an example. Suppose I have a signal from 20 hertz to 20 kilohertz. Okay. This is your audio frequency range. Okay. This we have discussed. Now, let's say it goes, it is, I transmit over 1,000 kilohertz carrier. Then, as we see later on, but just for your understanding right now, I will get a signal something like 1020 hertz, which is equal to 10000 hertz. Okay, so I will get this signal 1020 hertz, which is basically how it comes: 1000 kilohertz plus 20 hertz. Let's say uh, if I take the 20 hertz signal, so and this goes up to 1020 kilohertz, which is 1000 kilohertz, which we'll discuss later on how this thing. So basically my modulated signal, so I have a intelligent signal from 20 hertz to 20 kilohertz, a complete range. This complete range of the signal is overridden on the carrier. Let's say I choose a high frequency carrier, which is 1000 kilohertz. Now here 1000 lower frequency will become 1020 hertz, and higher frequency will become 1020 kilohertz. Okay, so this becomes my modulated signal range, modulated signal range, because this is also a range, but carrier is signal frequency. Okay, but now they are multiplex type of thing. So this is my modulated carrier. Why we have to sum up? Why we not multiply or something like that? That we'll discuss later on. But right now you assume we sum up these frequencies. So modulation means it is just summing up the two frequencies. When you say overridden, it is actually I'm summing up the two frequencies. I am adding the two frequencies, but because it is a range, so lower range translates to this frequency, higher range translates to 1020 kilohertz. But we'll understand mathematically also why modulation gives rise to the addition. Now, if you see here, so in my system, I have a low frequency and I have a high frequency. Now, if I take this ratio of highest to lowest frequency, it turns out to be 20 kilohertz supposed to be highest, my message signal, and 20 hertz was the lowest one, okay, of the message signal. If I see this message, my message signal was spread from 20 hertz to 20 kilohertz, so ratio was 1000. But if I see the ratio of corresponding highest to lowest frequency, of a modulated signal, okay. So this is please I'm trying to write as clearly as possible, but sometimes when you speak and write on something which you are not used to on the iPad and other thing, there is a slightly problem in the writing. So if you see this, it turns out to be something like 1020 000 was the highest one, and 1000 020 was the lowest one, and it turns out to be 1.01. So if I directly would have transmitted lowest message signal, the ratio was supposed to be 1000, okay, from highest to lowest frequency. But the moment I modulated it by passing over a carrier of 1000 kilohertz, the modulated frequency ratios turns out to be of 1.01. So basically, that means you need a large bandwidth signal, but here I need only a very small signal as compared to the this one. So that becomes my design simpler, because designing a wider band system is much more difficult than designing a narrow band system. So it is like I would say it is like it becomes a narrow band signal here, because the frequency range is not very much limited, and this becomes a wideband signal here. And designing the wideband systems is much more complex, because in basic electronics you must have designed an amplifier at 1 kilohertz, let's say, giving a gain of say 10 into 10 or into 20, and you easily get it. But the same amplifier, if you've been asked to design from 1 kilohertz to 100 kilohertz and giving the minimum gain of, let's say, into 20 at all the frequencies, it is not an easy thing. It is, so your design becomes very, very simple, as we see from this example. So these are the four main advantages of the modulation. So we discussed about what is modulation, I again stress that you are changing one of the parameters, frequency, amplitude, or phase of a carrier in accordance with the message signal amplitude. So there we only talk about the amplitude of the message signal. And this is modulation at in accordance with means at every instant. Okay. So sometimes again I can stress this. This is something if you've understood this definition, then we can easily move forward to. So here, which is the first slide, in instance, so I could say also here, sometimes I use this word quite often, in accordance with. Okay, or instantaneous value. That means where my amplitude of message signal is high, the corresponding parameter, either frequency or amplitude of phase, will be high. And that gives rise to the modulation. Then we discussed about the types of the modulation. As we discussed, either analog or pulse or digital, but we'll restrict ourselves to the analog part. And now we'll move to the concept of the mathematical understanding of the modulations in a big detailed way. Need for modulation we've understood. So now let's start mathematically understanding this parameter. Okay. So now we'll first talk about amplitude modulation. We'll start with amplitude, then we'll move to the angle modulation, which is basically your either the frequency or the phase. And because they are part of the angle, they are related to one another, as we'll see later on. But right now, we start with a new topic, which is called the amplitude modulation. AM. So I will use this word. Okay. So here I would say it is defined as the process in which the amplitude, okay, of carrier high frequency signal is varied in accordance with the amplitude of message. I'm again using that, but from next lecture, I will not be using high frequency or low frequency but right now I'm writing all the words that we normally use. This is what we call the modulating signal. At every instant. Okay. At every instant. So that we'll have to understand. So this is the amplitude. Here also it is the amplitude. This always remains the same, but this will change depending upon the how you define the modulation. Like if I have this thing as, if I change this thing to frequency, it will give rise to FM. If I change this thing to the phase, it will give rise to the phase modulation. But this always remains the message remains the amplitude. Now, because we have three signals, one is the carrier, another is the modulating signal. So we define two different things here. And this is what we call the linear modulation, angular modulation, angle modulation. And AM is also called the, as I told you, because it is not the angle one. So we define sometimes as a linear modulation. So amplitude modulation is also called the linear modulation, like angular. So this becomes the linear and angular. So this is the linear one. Again, as I told you last time, since your frequency is rate of change of phase, as we'll see later on, but we can write down. Normally, the frequency is nothing. It is basically how it is changing with respect to the phase. Okay. FM and PM are related to each other. That's why we normally use one of these modulation. And if you know, we have AM radio and FM radio, but we don't have the PM radio because frequency is nothing related to the phase by simply the rate of change of phase, which we'll discuss also later on when we talk about the phase modulation. Okay. So let's understand the mathematical concept of the phase modulation. Okay. Amplitude modulation. Representation of EM signals. So I am doing much more homework for you, writing each and everything so that you can refer to the notes anytime. So basically we have three signals. One is what we called a message signal. So now we have three signals in the modulation. One is, I write message signal, which is also called, again I am writing for your today's convenience, modulating or low frequency, or information signal. You have the degree in ICT, information and communication technology, or intelligent signal. So there are various words for that, but basically it is a modulating signal, and we represent as VMT is equal to VM sine 2 pi FMT. Right now I am ignoring the phase, ignoring the phase part for simplicity. Okay. Okay. So this is my modulating signal where M represents for modulating. So wherever you talk about, so this is the voltage amplitude of the modulating signal. This is the frequency of the modulating signal. And this is the final overall modulated signal, the AC one. Similarly, we have the other signal, what we call the carrier or high frequency signal. There is no other name for that. It is not a intelligent signal. It is just I used to over so that my message signal can be overwritten over that, and it was written as VCT. Now just to VC sine 2 pi FCT. Okay. Again, ignoring the phase part for simplicity. That is the theta. Okay. Now here, this C represents the carrier. So it is the voltage of the carrier, it is the frequency of the carrier, and it is the overall carrier's signal. Okay. So now because I have got two signals, then I will get a modulated signal. Now, how my modulated signal will look? My modulated signal will look as, this is my original signal, this is my carrier signal. So obviously, in this case, your FC is much, much greater than FM because intelligent signals are low frequency. Now, how my modulated signal will look? So AM modulated signal, so that is the final output. So modulated, which we normally say the final modulated. So this becomes my modulated. And because we are talking about the amplitude modulation, if you recall, I use this word here in one of the slides for the modulation, modulated. Let me see, where is that? Okay, I could not recall. So just why to waste time? I've already told you there is final output is called the modulated, which means it is a one signal overridden on the other signal. So because we are speaking in terms of the modulated signal, so a modulated signal, how it will look? It will look like this. See, I don't have to change the frequency and the phase here. I have to play with only the modulation amplitude only. So it could be written as VAM, okay, T is equal to VC plus see how I'm writing here. It is written as VC, that is the carrier wave amplitude, plus VMT sine 2 pi FCT. Now, please understand this. If I understand this, then other things will be very simple. This is amplitude modulation. So, which is nothing. Your message signal is overridden on the carrier signal. So, this is my complete message signal. This is my complete message signal. If you recall this expression, I write down as 1. This expression as 2 signals. Now, this was my original signal, VC sine 2 pi FCT. But my amplitude is changing in accordance with the message signal. So this is my complete message signal. So it has come in here, given by 1. The complete message signal. So my amplitude of the carrier, which was earlier VC, now it has become VC plus the entire signal, VMT. Okay, the entire message signal. Because I don't want to lose the message signal at all. It has got a certain frequency, it has got a certain amplitude, and it has got a certain phase. Everything should be transmitted as it is. And when we say everything is transmitted as it is, sometimes it is called a fidelity. You must have heard this word, which is slightly ahead of this. So this is what we call the fidelity. That means actual transmission or the reception of the original signal. So this word we use quite often. Wi-Fi, hi-fi. So that is phi basically denotes your fidelity. So fidelity here means you are actually getting the replica, means without the loss of genericity. So if you notice here, the entire message signal has become part of the amplitude. So this becomes the amplitude of the modulated carrier. So here, VC plus VMT, that becomes my amplitude of the modulated carrier. Recall that amplitude of the carrier was simply VC, but it has got VMT. So I could write down this thing. Let's further this thing. So from 1, I could say, I could write the mathematical expression. See, it is very simple now. VAMT is equal to VC plus VM sine 2 pi FMT sine 2 pi FCT. So that becomes my a modulated wave. Just to give some example for you, what it means. Okay. Let's take an example. I always believe in examples. So you understood. So that means the entire, this becomes my, this is nothing. It is your VMT. Okay. So this becomes my, I am not playing with the frequency or the phase part. It remains as it is. I am playing only the amplitude part of the carrier, which has now been modified from VC to VC plus VM sine 2 pi FMT. And please note the difference between the small letters and capital letters. Okay, I could have given you the notes or something like that from the book, or I could have asked you to refer to the book, but they don't stretch such things. That's why I am writing each and every step for you and asking you to refer to these notes only. Because here I'm stressing certain things which are not actually given stress upon, but which are very important. Like DC amplitudes are represented only in the capital letters. Otherwise, the complete signal is represented by a small letter. Now, this becomes my expression for the AM. Let's do one example, how this thing takes place. So I take one example. Suppose I have a carrier signal, which is given as VCT is equal to 5 sine 2 pi into 10 to power 6 t. Okay. So I've got a Fourier signal and it is modulated by a modulating sinusoidal signal only. Right now I'm assuming sinusoidal, which is given as VMT. Let's say it is given as sine 4 pi into 10 to power 3 t. Okay. So this is the one. So my question is, what is the expression for resulting AM signal? Okay. So here, if you solution, how we could go for that? It is simply, it has to be in this form, which is VAMT is equal to VC plus VMT sine 2 pi FC T. So in this case, it becomes, now VC was how much? If you see, VC here is, this is your VC. So it becomes 5 plus your VM remains the same. This I could write as 1, which is nothing. It is VM. So it is, in this case, it becomes sine 2 pi FMT. 2 pi FMT. So this becomes sine 4 pi. It remains the same. Sine 2 pi into 10 to power 60. So that becomes my solution for the modulated way. Simple. So this is how we go for this one. Sometimes when you do the lab experiment, okay, वो भी हम लोगों को देखना है, because this is a problem which is related to your lab also. We normally do the hardware and the software in both the for AM also in our lab, but because of the online, we'll have only the software based AM lab, but we can understand this thing also better using the software. So if a lab based example, if I take one more example of this one, which is slightly different. Sometimes we talk about the RMS value, because you must have noticed there is a RMS voltage and there is a peak voltage. Okay. So in the labs and everything, we measure the RMS voltage. So the example is like this. Suppose I have got a carrier signal with an RMS voltage. RMS voltage basically is nothing. It is called the root mean square. Okay. Or voltage, or it is also called the effective voltage. Okay, but more commonly known as RMS voltage. Okay, I will explain to you. And it is related to the peak voltage, because whenever we talked about the DC amplitude, we talk about the maximum value or the peak value. So now here I have a slightly different problem. I have got a carrier signal with RMS voltage of 2 volt. Now this is important. I'm not talking about the peak volt, okay, and frequency of 30 megahertz is amplitude modulated with a frequency of 500 hertz. Obviously, it is quite small as compared to carrier frequency 30 megahertz and maximum amplitudes. So here I'm just giving one example, but there are two signals. One is carrier signal, where I'm talking about the RMS voltage, not the maximum voltage. But in our expression, we normally use the maximum voltage. And another signal, which is a low frequency signal, is of 500 Hz, but we are talking about the maximum amplitude. So in this case, how to write the expression for AM wave? Last time we have both the wave expression. Now here we don't have the expression. So we have to write the expression for each of these waves. So how to go for this? Now please note that your VRMS, or what we call V effective, is equal to V naught by root 2, or Vm by root 2. That is the maximum or peak value. So that is the relation. Please remember this relation. If we are encountering, because in the lab we normally measure the RMS voltage, but finally the expression you have to use the maximum or the peak voltage, which means your Vm maximum, here it means maximum, okay, is equal to V naught is equal to under root 2 VRMS. Okay, so that is the expression we have to use. So for this carrier frequency, which has got a voltage of 2 volt, so for carrier already given is FC is given as 30 megahertz. Okay, so we normally convert into hertz, so it becomes 30 into given, and VC is equal to under root 2 into VRMS, which is right here, VRMS. So that turns out to be under root 2 into 2. So that is around 2.8 volt. Okay. So that becomes my expression for VC. So your VC becomes like VC sine 2 pi FCT. So it becomes 2.8 sine 2 pi into 30 into 10 to the power 6t. So that becomes my expression for VC, which was given directly like that in the previous example. And for message signal, FM we have already got. It is a low frequency. It is given as something, what frequency I have taken? 500 Hz. So no need to convert. It is already given to you as 500 Hz. And here already we have given the maximum value, which is 1.4 volt. So it is already a maximum or peak value. So no need to change. So I could write down this as Vm. So you can write as VCT, VCT. VMT, basically the time domain expression. So we always write T in the bracket here. So this expression becomes something like 1.4 sine 2 pi into 30, 500t. Okay, straightforward. You can actually solve it also, but I'm not solving it completely. That means you can multiply 2 pi into 500, so 1000 pi and all those things. So your expression for VAMT, which is given as, how it is given as, we have already understood, VC plus VMT sine 2 pi FCT. So in this case, this is the expression we already know for that. So in this case, my VAMT, just how I'm writing, capital letters and everything, 2.8 plus 1.4 sine 2 pi into 500t sine 2 pi into 30 into 10 to the power 6t. So that is one. Now you can further solve it. 2 pi into 100, 500, you can put 1000 pi. and this also 2 pi into 36 into this one, you can go for this. So this is my expression which we got it, and this is the solution for that. So sometimes we don't write the expression, but you can always with the values given. So you have to make a note that if you are measuring the RMS voltage, convert into the peak voltage, which is called the effective voltage or the uh, root mean square voltage. So it is nothing. It is V naught by root 2. Okay. Then the next parameter which we introduce here. So these are the two examples. As I said, I will take few examples only, but very, very clear. And now you can solve any problem of any type. Okay. In one problem, I have not given the expression for the mathematical expression for the voltage for the message and the carrier signal, but we can write from that values. Now the third parameter which we are going to introduce from is what we call the modulation index. So it is basically related to the AM only. Everything is about AM. And this is nothing we define as MA, small ma. So what is this? It is nothing. It is your ratio of, and this is very important to understand why this modulation index, maximum amplitude. I am writing the short form of message signal, which I said is already a low frequency signal and denoted as VM to the maximum amplitude of, and it's got a good number of significance. That's why we have to define this carrier signal. What is the amplitude of the carrier signal? Maximum amplitude we define as VC. So this is what we call the modulation index of AM wave, amplitude modulated wave. Okay. Now so basically your I would write down this MA is equal to VM over VC. So this is one thing we have to understand. It is also called, sometimes various books talk about various meaning, modulation depth, depth of modulation or modulation depth. Okay. Also called coefficient of modulation. Okay. See, modulation we always do in our speech. Sometimes we modulate our voice. मैं कभी ज़्यादा amplitude बोलूँगा, so that means I am changing the amplitude. So that means I am modulating my voice so that it goes to you properly. Sometimes I speak very fast, or sometimes I very speak. That means I am changing the frequency of the my signal. So, and how much I could change, that becomes my modulation index. Okay, because I could change the frequency, I could change the amplitude, I could speak very fast, very slow, but I'm changing the frequency. So that is defined by, we'll understand slightly better, it's called modulation index. So depth of modulation, coefficient of modulation, sometimes it is also called modulation factor also. And it's got no units because it is a unitless or dimensionless quantity because both are voltage by voltage. So it is a factor. Or sometimes it is called, for the amplitude modulation, it is called the amplitude sensitivity also, but very rarely used. But various meanings are there. Typically, this modulation index is expressed in terms of percentage. Normally, it is expressed in terms of percentage. So if I got VM over VC, let's say 0.5, or VM over VC, let's say 1, so it becomes 1%. If I say VM over VC, that means both are same, VM equal to VC, or it could be like 1 by 2, that means 0.5. So that means 50% modulation. So it is normally expressed in terms of what we call the percent modulation. And percent modulation means capital MA. And this is nothing, it is MA into 100%. Okay, so that is how we define the percentage of modulation, because we normally speak in terms of this one. Let's do one example based on that before we wind up for today's lecture and start with the more mathematical understanding of the AM. So one example we'll do based on this. Suppose I got a carrier signal. Let's say it is given as VCT is equal to I take let's say 2.8 sine 2 pi into 36 into 10 to the power 60, and message signal, let's say, is given as VMT is equal to 1.4 sine 2 pi into 500 t. So we have to determine modulation index and your percent modulation. So how to go for that? Now here, what we go for that? MA is equal to VM over VC. So this is my VM, this is my VC. So it becomes 1.4 by 2.8 volt. So that means 0.5. And percentage of modulation becomes point that we have already understood. It is expressed in terms of percentage MA into 100. So it turns out to be 0.5 into 100. That means 50%. So that means, so it has got a significance. How much we should modulate? 50% से क्या होता है? उससे क्या होता है? And like that. So this is how we calculate. Sometimes we give the expression like another problem. Suppose I have VCT is equal to, let's take this example only. Sorry, I have to rub this. 2.8 sine. I would go for sorry. Let's say 60 into 10 to power 60. That is 60 megahertz. So 60 pi. Sorry. It clearly. Okay. So in this case, I am asking what is the FCT. So obviously the solution is simple. Sometimes we write completely. अभी तक तो हम लोगों ने सब अलग करके देखा है. So solution ये है 2 pi FCT is equal to 60 pi into 10 to power 60, which means your FC becomes 30 into 10 to power 6, which is 30 megahertz. Okay, so that is what we have seen. It is nothing, it is your FC. Okay, so sometimes we write the complete one, but from there you can actually find out what is the FC. So please make sure that if something is given like 60 pi into 10 to the power 6, it doesn't mean your FC is 60 pi into 10 to the power 6. Your FC turns out to be 30 megahertz. So that is also another way of changing the problem, that instead of sine 2 pi into 36 into 10 to the power 60, if I write very clearly, उसमें clear आ जाता है FCT, but otherwise you have to work out. So with this, I stop it here, and I will share these notes. Please don't worry, all these slides, PDF files, in my next lecture. Once I have not yet got the list, I am rewinding them. Maybe I get in this thing. When I form the group, I will share this thing slides with you. And I'm trying to do the recordings also, whichever is possible. But the size is too big. Also, it will be shared in the shared drive folder, which will be shared with you. So we'll learn something more mathematical understanding of the concept of the modulation index. What is the significance of that? What is the significance of the depth of the modulation or the modulation index and so on. So there could be something like overmodulation, what will happen then and all those things. So we'll discuss in my next lecture. So I stop my presentation here and save the slide for you. Okay then. Any questions? No questions in the chat box? Any query? Not yet. So I'll stop it here. I will end my meet.